My dear students, welcome back to our channel. In this video, I will be explaining the BSc third semester subject Chemistry as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 4 first important short question is: what are significant figure? Give their importance. Significant figures, SF, and their importance. Significant figures are the digits in a number that carry meaningful information about its precision. They include all certain digits plus the first uncertain digit. SF helps scientists communicate how accurate and reliable a measurement is. Example, if a mass is recorded as 12.34 g, all four digits 1, 2, 3, 4 are significant. The last digit 4 may have a small uncertainty, but it's still important. Importance: 1. Accuracy and precision. SF show how exact a measurement is. 2. Consistency in calculations. Using correct SF avoids overestimating precision. 3. Error minimization. Helps in reporting data without misleading accuracy. 4. Scientific communication. Ensures everyone understands the reliability of data. Quick tip: non-zero digits are always significant. Leading zeros are not, and trailing zeros in decimals are significant. Example to remember: 0.00450 only 3 SF, 4, 5, 0. Think, ignore leading zeros. Count meaningful ones. Next important short question is: 2. What are accuracy and precision? Accuracy and precision. Accuracy tells us how close a measured value is to the true or accepted value. If your measurement is near the real value, it's accurate. Precision tells us how close repeated measurements are to each other, regardless of whether they are correct or not. High precision means the results are consistent. Example, suppose the true weight of a substance is 10 g. If your three measurements are 9.8 g, 10.1 g, and 9.9 g accurate and precise, close to true value and consistent. If measurements are 8.0 g, 8.1 g, 8.0 g precise but not accurate, consistent but far from true value. If measurements are 9.0 g, 10.5 g, 11.0 g neither accurate nor precise. Easy tip to remember: accuracy is equal to right on target. Precision is equal to close together. Both are important in experiments to ensure reliable and trustworthy data. Next important short question is: 3. State Gibbs phase rule and define the terms phase and component. Give an example for each. Gibbs phase rule. Gibbs phase rule helps us predict the number of variables, like temperature, pressure, and composition, that can be changed independently in a system at equilibrium. The rule is given by F is equal to C, P plus 2, where F is equal to degrees of freedom, number of independent variables. C is equal to number of components, chemically independent substances. P is equal to number of phases, physically distinct states. Definitions: 1. Phase, a physically and chemically uniform part of a system. Example, ice, water, and steam are three phases of HO. 2. Component, a chemically independent substance in a system. Example, in a NaCl HO solution, NaCl and HO are two components. Example, for a one-component system like water, ice, liquid, and vapor at equilibrium. F is equal to 1 to 3 plus 2 is equal to 0. This means no variable can change at the triple point, it is fixed. Easy tip to remember: F is equal to C, P plus 2 tells you how free you are to change things in equilibrium. Next important short question is 4. Explain aldol condensation with mechanism. Aldol condensation. Aldol condensation is a reaction where two molecules of aldehyde or ketone combine in the presence of a base to form a beta-hydroxyaldehyde or ketone, which may dehydrate to give an alpha-beta-unsaturated carbonyl compound. Mechanism: base catalyzed. 1. Formation of enolate ion, base, like O, removes an alpha hydrogen from the aldehyde ketone, forms enolate ion. 2. Nucleophilic attack. Enolate attacks the carbonyl carbon of another molecule, forms beta-hydroxyaldehyde ketone. 3. Dehydration. Optional on heating. Beta-hydroxy compound loses water, forms alpha-beta-unsaturated aldehyde ketone. Example: two molecules of acetaldehyde, CH2, react in NaOH, forms 3-hydroxybutanol, which on heating gives crotonaldehyde, CHCH is equal to CHO. Easy tip to remember. Think aldehyde plus aldehyde hydroxy unsaturated. Aldol is equal to aldehyde plus al hydroxy. It's widely used in organic synthesis for making flavors, perfumes, and intermediates. Next important short question is 5. Write a short note on desilverization of lead by Pattinson's process. Desilverization of lead by Pattinson's process. Pattinson's process is a method to separate silver from lead in a lead-silver alloy. It works because lead and silver have different melting points. Process: 1. The molten lead-silver alloy is slowly cooled in a series of iron pots. 2. As it cools, pure lead crystallizes first because lead has a higher freezing point than silver. 3. These lead crystals are removed from the pot. The remaining molten lead becomes richer in silver. 4. This process is repeated in multiple pots to concentrate the silver in the final molten portion. Example: lead with 1-2% silver can be enriched to 10-20% silver using this method, which is later refined by cupellation. Easy tip to remember. Cool the alloy, lead freezes, silver left behind. It's an old, simple, and cost-effective method for desilverization before modern electrolysis. Next unit 4. Long questions. First important long question is: what are errors? Explain about types of errors. Errors in analytical chemistry. In experiments, errors are the differences between the measured value and the true or accepted value. They are unavoidable but can be minimized by careful work. Understanding errors is important for accurate and precise measurements. Types of errors. Determinate systematic errors. These errors have a known cause and are consistent in one direction, always high or low. Causes: faulty instruments, improper calibration, personal bias, or wrong method. Example: a balance that reads 0.05 g more than the true weight. Correction: can be reduced by calibration or correcting calculations. Indeterminate, random errors. These errors occur unpredictably and vary in magnitude and direction. Causes: environmental changes, human reaction time, minor fluctuations in instruments. Example: fluctuating readings in a thermometer due to slight temperature variations. Correction: cannot be completely eliminated but can be minimized by repeating measurements and taking the average. Subtypes of errors often discussed. Absolute error, delta x, difference between measured value and true value. Delta x is equal to x measured, x true. Relative error, absolute error divided by true value, expressed as a fraction or percentage. Relative error is equal to delta x, x true times 100. Example to remember. If a substance's true mass is 10.0 g, measured mass is equal to 10.2 g, absolute error is equal to 0.2 g. Relative error is equal to 0.10 times 100 is equal to 2%. Easy tip to remember. Determinate is equal to predictable, correctable. Indeterminate is equal to random, average out. Errors are inevitable in all experiments, but understanding their type helps us report data reliably and improve experimental results. Next important long question is: to explain mean, median, range and standard deviation. Mean, median, range, and standard deviation. In analytical chemistry, statistical tools help us analyze data and measure accuracy and precision. Mean, average. It is the sum of all observations divided by the number of observations. Formula. Mean x is equal to x underscore I n. Example, if 5 masses are 10, 12, 11, 13, 12 g, then mean is equal to 10 plus 12 plus 11 plus 13 plus 12, 5 is equal to 11.6 g. Median. The middle value when data is arranged in ascending or descending order. Example, data is equal to 10, 11, 12, 12, 13, median is equal to 12 g. Range. Difference between the maximum and minimum values. Formula. Range is equal to x max x min. Example, max is equal to 13 g, min is equal to 10 g, range is equal to 3 g. Standard deviation, SD. It measures how far individual values deviate from the mean, showing data spread or precision. Formula. SD is equal to 11x 2 n 1. Example, for 10, 12, 11, 13, 12 g, SD 1.14 g. Easy tip to remember. Mean is equal to average central value. Median is equal to middle not affected by extremes. Range is equal to max min spread. SD is equal to spread around mean precision of measurements. Importance. These tools help analyze experimental data, identify errors, and improve accuracy and reliability in results. Next important long question is: what are carbanions? Explain the factors influencing the stability of carbanions. Carbanions and factors affecting their stability. A carbanion is a carbon atom that carries a negative charge with 3 bonds and a lone pair of electrons. Because of the extra electrons, it is a nucleophile and can react by donating this pair in chemical reactions. Example: CH3, CCl3-, CH2 COH3. In CH3-, carbon has a negative charge and 3 hydrogen atoms bonded to it. Formation of carbanions. Carbanions are formed when a slightly acidic hydrogen is removed from a carbon atom by a strong base. Example, deprotonation of ethyl acetoacetate. CH3 COH to CO8 plus or CH3 COH, CO8 plus H2O. Factors influencing stability. Electronegativity. Higher electronegativity stabilize the negative charge. Example, carbon in sp hybridized alkynes is more stable than sp superscript 3 carbon. Resonance stabilization. Delocalization of the negative charge over multiple atoms increases stability. Example, enolate ion CH2, COH3 is stabilized by resonance with the carbonyl group. Inductive effect. Electronegative atoms near the carbanion withdraw electron density, stabilizing the negative charge. Example, CCl3 is more stable than CH3 because chlorine atoms pull electron density away. Hybridization. Carbons with more S character hold the negative charge closer to the nucleus, stabilizing it. Order: sp sp superscript 2 sp superscript 3. Solvent effect. Polar protic solvents, like water, alcohol, stabilize carbanions through hydrogen bonding. Easy tip to remember. Resonance, induction, electronegativity, hybridization, solvent reaction. Importance. Carbanions are key intermediates in important organic reactions like aldol condensation, Perkin reaction, benzoin condensation, and in forming higher alkynes, making them essential in organic synthesis. Next important long question is: 4. Discuss the following reactions with mechanism. I. Haloform reaction. 2. Benzoin condensation. I. Haloform reaction. The haloform reaction is a reaction in which a methyl ketone, CH3COR, reacts with halogens, Cl, Br, or I, in the presence of a base to give a haloform, CHX3, and a carboxylate salt. General reaction. CH3COR plus 3X2 plus 4O CX3 plus RCO plus 3H2O. Mechanism: simple steps. Halogenation of alpha hydrogen. The base removes an alpha hydrogen from the ketone. The resulting carbanion attacks the halogen to form CHX2COR. Repeated halogenation produces CX3COR. Cleavage. The base, EO, attacks CX3COR, breaking the C to C bond to form CX3, which picks up a proton to give CX3H, haloform, and RCO, carboxylate. Example: CH3 COT 3 plus I2 plus 4 now H, Chi3 plus CH3CO na plus 3H2O. Easy tip to remember. Methyl ketone plus halogen plus base haloform plus carboxylate. 2. Benzoin condensation. Benzoin condensation is a reaction where two molecules of aromatic aldehyde, like benzaldehyde, combine in the presence of cyanide ion, Cn, to form benzoin. Reaction: 2C6H5CHO, KCN, C6H5CH, or CO, C6H5. Mechanism: simple steps. Nucleophilic attack. Cn attacks the carbonyl carbon of benzaldehyde forming a cyanohydrin intermediate. Carbanion formation. The alpha hydrogen is acidic. Cn removes it to form a carbanion. Attack on second aldehyde. This carbanion attacks another benzaldehyde molecule forming a new C to C bond. Elimination of Cn. Cn leaves, regenerating the catalyst, giving benzoin. Key points to remember. Cn acts as a catalyst. Two aldehyde molecules are required. Forms alpha hydroxyketone, benzoin. Easy tip to remember. Benzaldehyde plus Cn benzoin. Cn helps form carbanion, attacks another aldehyde alpha hydroxyketone. These two reactions are important examples of carbanion chemistry, showing how stability and nucleophilicity of carbanions help form new bonds. Next important long question is: 5. Explain and draw the phase diagram for NaCl-HO system. Label it and discuss the importance of various points, lines and areas in equilibrium. Phase diagram of NaCl-HO system. The NaCl-HO system is a one-salt-water system showing the equilibrium between solid NaCl and its aqueous solution at different temperatures and compositions. Key terms. Phase, a physically distinct form of matter, solid NaCl or liquid solution. Component, chemically independent substance, NaCl and HO. Degree of freedom, F number of variables, temperature, pressure, composition, that can be changed without changing the number of phases. Gibbs phase rule. F is equal to C, P plus 2. For NaCl, HO, C is equal to 2, NaCl and HO, P is equal to 2, solid plus liquid at equilibrium, so F is equal to 2 plus 2 is equal to 2. This means two variables, temperature and composition, can be changed independently along the phase boundary. Diagram explanation. X-axis, composition of NaCl, % by weight. Y-axis, temperature, degree C. Solidus line, boundary between solid plus liquid and only liquid region. Liquidus line, upper boundary of the liquid region. Point A, pure water freezing point, 0 degrees Celsius. Point B, saturated solution, solubility limit, tilde 26.4% NaCl at 0 degrees Celsius. Below solidus, only solid NaCl exists. Above liquidus, only liquid solution exists. Between solidus and liquidus, solid and liquid coexist, equilibrium region. Importance of diagram. 1. Shows solubility of NaCl at different temperatures. 2. Helps in crystallization processes to obtain pure NaCl. 3. Explains equilibrium between solid and saturated solution. 4. Helps in industrial salt production from brine. Easy tip to remember. Solid plus water solution, check where lines meet equilibrium. Solidus is equal to start melting, liquidus is equal to fully liquid. Visual. Temp, degree C. Liquid. Dash liquid plus solid. Solid. Composition, % NaCl. This diagram shows the relationship between temperature, composition, and phases clearly and is important for phase equilibria and industrial applications. Next important long question is 6. Explain and draw the phase diagram for one component water system. Label it and discuss the importance of various points, leans and areas in equilibrium. Phase diagram of one component water system. A one-component system consists of only water, HO. Its phase diagram shows the equilibrium between solid, ice, liquid, water, and gas, steam, at different temperatures and pressures. Gibbs phase rule. F is equal to C, P plus 2. Here, C is equal to 1, water, P is equal to number of phases, 1, 2, or 3, and F is the number of variables, temperature, pressure, that can be changed independently. Single phase regions, F is equal to only ice, water, or steam exists. Both temperature and pressure can vary freely. Two phase regions, F is equal to 1 solid plus liquid, liquid plus gas, or solid plus gas coexist. Only one variable can change independently. Triple point, F is equal to 0 solid, liquid, and gas coexist at 0.01 degrees Celsius and 0.006 atm. No variable can change independently. Diagram explanation. X-axis, pressure. Y-axis, temperature. Lines. Solid, liquid line, melting freezing points at different pressures. Liquid gas line, boiling points at different pressures. Solid gas line, sublimation points. Important points. 1. Triple point, ice, water, and vapor coexist. Unique T and P. 2. Critical point, above 374 degrees Celsius and 218 atm, water becomes supercritical, liquid and gas are indistinguishable. 3. Sublimation region, solid gas without becoming liquid, ice to vapor. 4. Melting point line, shows pressure dependence, ice melts under higher pressure. Importance of diagram. Explains phase changes, melting, boiling, sublimation. Helps in industrial applications like steam engines, refrigeration, and supercritical water processes. Shows effect of pressure on phase changes, useful in high-pressure science. Easy tip to remember. Triple point is equal to all three phases together. Critical point is equal to liquid plus gas become 1. Lines is equal to where two phases are in equilibrium. Visual. Pressure. Gas. Liquid. Solid. Temperature. This diagram is fundamental for understanding phase equilibria in water and helps explain many practical and industrial processes.